Good morning. Is it audible? Akshata.
Yes,
In the previous class, we were discussing about memories, model number 3. In that, we discussed what is the use of memories and what are the different types of the memories. Okay. Here, that we go through this problem here. If a memory has 32,768 location, each of 32 bits, what is the total capacity of the memory and how many address bits does it requires? Okay, it's very important here. Please note down this here. How many locations? 32,768 locations. I will use here, I will draw the diagram here, then you will get it. Just remember here. Just remember, this is the memory block. These are each locations here. Sorry. Okay. 0 to how many? The each location address starts from 0. Here 0 to 32,768. That means 32,000. 7. Sorry, here I will write here. 32,767. How many locations? 0 to 32,767. Okay. Each bit which can hold each location which can hold 32 bits here, where here each location 32 bit. That means 32 into how much? 32,767. That means here that we should tell how many number of the bits it can hold. That means here each location which can hold 32 bit. How many locations? 32,768. That means here they mentioned here 32,768 locations. That means it's 2 to the power of 15. The memory requires how many address here? 15 address. How many locations? 32,768. Okay, that is equal to 2 is to 15. That power is the 15 address bits. Okay, the total capacity. The total capacity is 32,768 into 32. That means how much it will? It becomes 10,48,576 bits. It's the total capacity is it's the 2 raised to 20 bits. Okay. Similarly, I will do some kilo. What is kilo here? 2 is to 10. 2 is to 10 means here which can the memory which can hold 10,024 memory locations. Okay. Similarly, mega. Two is to 20. That means 10,48,576. That means this is the example. This is mega here. Okay. Then giga is 2 is to 30. That means 1024 into 2 is to 20. That means this is the memory size here. Okay. Then the 1 megabit memory might be organized as 32K into 32 bits. Okay. Or 16K into 64 bit. Here you can multiply it. 32K into 32. How much? 32,000 into 32. See how much it becomes? 1 mega. That means 10 lakh, right? 10,48,576 bits. Yeah, we can organize it like this. Uh, 32K 32 bit or 16K 64 bit. Okay, I can multiply 32K into 32 bit. That means here each memory which can hold 32 bit. Okay, here in 16K into 64 bit, 16K memory locations, each location which can hold 64 bit. Okay, then this is the memory block. Okay, you can consider here. Sorry. See, here there are two basic operations. One is A inputs. These are the A inputs, unsigned address. Okay. Then D in and D out. Type depends on applications. Okay. Here, first one, write operation. Okay, what are the conditions? Here, enable and WR. These are the control signals here. Okay. When enable equal to 1 and WR equal to 1. Okay, what will happen? The write operation is enable. Write operation is enable. Here D in value stored in location given by address inputs. Okay. Then during the read operation, what will happen? It will be changed. Enable equal to 1 and WR equal to 0. Okay. Then D out driven with value of location given by address inputs. Okay. Here the when enable equal to 1 and WR equal to 1, okay, what will happen? The write operation will take place. Okay, enable equal to 1 and WR equal to 0. Which operation? Anybody? Which operation will take place? Read operation. Okay, who is online here? Akshata. What are the conditions for read operation and write operation? Hello? All of you unmute your speaker. All of you unmute your speaker. Okay, and here enable equal to 0 means it's in idle state. Enable equal to 0 means it's in idle state. Okay, here this is some problems here. Then we'll just remember this block, memory block. Okay, symbol for basic memory component. Okay, which can consist of address memory, data location, okay, input data and output data locations. Okay. Just remember, enable equal to 0 means it's in idle state. Okay, this is some problem. How can conduct the memories? See here, 16K 48 bits. 16K 48 bits. 16K 48 bits. See here, here we can construct this one using 3 memory blocks. We can construct this using 3 memory blocks. Here 16K cross 16 bit. 16K cross 16 bit. That means here each output, first output here 16 bit, and here 16 bit, and here 16 bit. Okay, the memory block same here. What are the control signals? Enable, WR, address bits. Okay, then D in, it's a input bit. Okay, Here 16K 64-bit memory can be constructed using three 16K 16-bit memory components as shown above. This one using 16K cross 16-bit. 16K cross 16-bit. Okay, just multiply here. Uh, just multiply here. 16K into 16-bit. How much it's? Please, anybody please talk. 16K into 16. How much? It's 2,56,000. 2 lakh. Is it audible now? Hello?
Yes, sir, audible.
Yeah, okay. See here, 16K into 16-bit. 16K into 16-bit. Actually, first you can multiply here. How much? 16,000 into 48. 16,000 into 48-bit. How much it will? Just check it. 7,68,000 bits. That is the total capacity of the memory. But here we are constructing 16K into 48-bit memory using 16K into 64-bit. Here 16K into 16-bit how much? 2,56,000. Okay, what is the total capacity here? The total capacity is around 7 lakh, right? Around 7 lakh. From this, we will get 2,56,000. From this, we will get 2,56,000. From this, we get 2,56,000. Here we can get the 16-bit data. Here the 16-bit data. Here the 16-bit data. Then how much? What will happen here? We'll get the 48-bit, right? 16-bit here, 16-bit here, and 16-bit here. We are not getting 48-bit from only a single memory. Okay. One more problem to discuss here. One more is 64K into 8-bit. 64K into 8-bit memory using 16K into 8-bit components. Here, what is the output here? What is the output? Output 8-bit, right? But here also we are getting 8-bit. Here also 8-bit. Here also 8-bit. Then I will get the remaining data. See here. What it did here? 8-bit from this memory, 8-bit from this memory, and 8-bit from this memory, and 8-bit from this memory. See here, 64K, how many locations here? What is the number of locations? 64K, right? This one. 64K locations. Here you can get the log of 64,000. Log of 64,000. Yeah, wait a minute here. Wait a minute. Voice is audible? Hello?
Yes, sir.
Yeah, okay. Wait a minute, I will show you how to calculate the address and all. Yeah, what is the value of log of 64? Just check it. Log of 64 and then divided by log of 2. That means here 15 addresses. 15 addresses. See here, output is 8-bit. Here also, when you divide the memory, there also 8-bit. Then what we can do here? From this memory block, we'll get 8-bit. From this block, 8-bit, or from this block, 8-bit. And also 8-bit from this block. The memory symbol is same. Okay, right signal is there, address and the in. Okay, but here the what is the memory block memory locations here? 16K, right? Then 16K log of 16,000 divided by log of 2. That means 14 bits. That means the each memory block is 14 bits. Here 16K into 8-bit. I hope it's clear. Total for this 64K, the address bit is 16-bit. For 64K, address bit is 16-bit. But here we have the memory block is 16K. For this 16K, log of 16K divided by log of 2. It will become 14. But what is the memory total memory? Sorry, address bits is 16-bit, right? Here 14 bits the address bits. Remaining 2 bits, that means 15 and 14. Okay, that can be used for selecting the output line. See here, they mentioned here. The address bits 15 and 54. Address bit 15 and 54. There's a problem with some mouse here. This 15 and 14 are decoded to select which of the 4 memory components is enabled for read and write operations. See here how we can calculate the address bits. How many number of the address? 64K. That means log of 64,000 divided by log of 2. How many bits? 16 bits. But here we are constructing this one using 16K 8-bit. Okay. For 16K, what is the number of address bit? Log of 16,000 divided by log of 2. That means 14 bits. Here 14 bits used for address. Okay. Then remaining 2. AF15 and AF14 address bits. See here. Address bits 15 and 14 are decoded to select which of the 4 memory components is enabled for read and write operations. Okay. This is about the memory construction. Some problems here we'll discuss. 256M into 16-bit memory by using 4 256M into 4 bits. See here, memory location 256 here also same, here also 256. But here 16-bit output. Okay, But here using this bit, we'll get only 4 bit. Remaining, how many bits left here? 12 bits, right? Then one more 256 mega into 4 bit, 8 bit will get. 256 into 4 bit, 12 bit. Okay, 256 mega into 4 bit. How many bits we got it here? How many bits we got? Totally 16 bit outputs. Okay, we connect in series, same as this one, this problem only. I'll show you. Same as this problem. Not this one. Yeah, this one only. This one only. Okay, let's go through this. Here a bit, here one more, next problem here. This is about 256 into 16 bit. In parallel, you can connect 256 into 4 bits memory in parallel 4 memory blocks. Okay. Next one is design 1 giga into 8 bit memory by using 256 mega 8 bits. Okay. So here this is almost example of this one. Same as this one. Okay, here 1 giga, that means how much? Around 10 lakh memory bits capacity. Okay, but here we are using 256, that means 4 for 256 memory blocks we connected in parallel. Okay, here also output is 8 bit, here also output is 8 bit. Then what we can do here? We can use the multiplexer. Okay, log of 1 giga divided by log of 2, find out that value. Okay, log of 256 mega divided by log of 2, you can check it. How many address bits you will get? You can use it. Whatever the remaining bits here, for example, you can consider here we get 14 bits, here we will get 16 bits. Okay, these 14 bits used for this memory location. So remaining bits are selective address here. To select the output lines, we can use it. Okay, just remember that. Then the next one is design of 64K into 16 bit. Design of 64K into 16 bit. Here, composite memory using 16K into 8 bit component. 16K into 8 bit. Here, what is the output here? 16 bit. What is the output here? 8 bit. Okay, just go through this one. Next here we'll discuss about the memory types. Memory, random access memory, read only memory. Random access memory and read only memory. Here, what is meant by the random access memory? Anyone? What is meant by random access memory? What is meant by random access memory? Random access memory is a volatile memory. What is meant by the volatile memory? If the power is off, it will hold the data or not? No.
Short-term memory, sir.
Pardon?
Hello.
What is the use of random access memory? It's called volatile memory. Why? Hello? And the power is off, okay, it will hold the data or not? No. What about the read-only memory? When power is off, okay, again it can hold the data. Okay, then random access memory, you can do the read and write, both purpose. With the read-only memory, you can only read the data. Okay, Again here, classify random access memory as asynchronous static RAM, synchronous static RAM, and dynamic RAM. Okay, asynchronous RAM, static RAM, synchronous static RAM, and dynamic RAM. Okay, today we'll discuss about the asynchronous static RAM. Okay. A minute. Next, we will discuss asynchronous random access memory. Yes, we call it as SRAM. Here, asynchronous SRAM. From here, we will start it here. One of the simplest form of memory is asynchronous static RAM. It is asynchronous because it is not really, that means dependent on clock for its timing. It is not dependent on the clock. That's why we call it as asynchronous. Okay. The term static means that stored data persists indefinitely so long as power is applied to the memory component. Here, what is the mean by the data is hold as long as power is applied to the memory. What type of memory? It's a volatile memory. What do we call? We call it as a volatile memory. See here, it is volatile. It is volatile, meaning that it requires power to maintain the stored data and loses data if power is removed. That remember, random access memory are volatile memories. Okay, random access memory are volatile memory. Asynchronous SRAM internally uses 1-bit storage cell that are similar to the D latch. Here, asynchronous SRAM internally uses a 1-bit storage cell. Okay. Then within the memory, see here, within the memory, component, the address is decoded to select a particular group of cells or enabled that comprise one location. The memory component, the address is decoded to select a particular group of cells. It means here this one is consist of C here. The Synchronous SRAM internally uses 1-bit storage cell that are similar to the D-latch circuit. Within the memory component, the address is decoded to select a particular group of cells or enabled that comprise one location. See here, what about the write operation? For a write operation, the selected latch cells are enabled. Selected latch cells are enabled and the input data is stored during the write operation. During the read operation, for a read operation, the address activates a multiplexer that routes the outputs of the selected latch cells to the data outputs of the memory component. For a read operation, the address activates a multiplexer. That means here at the output side, we have the multiplexer. The multiplexer which can select from which memory block we can fetch the data. Read means which can fetch the data. Okay. For a read operation, the address activates a multiplexer that routes the outputs of the selected latch cells to the data outputs of the memory component. Then here, asynchronous SRAM are usually only available as packaged integrated circuits. That means IC, packaged integrated circuits. Later in first module, this is what is meant by the packaged integrated circuits. It's a IC. It can be available as a IC. Okay, not as blocks in SIC libraries or FPGA. Okay. Okay, one more thing we'll discuss here. Yes.